Hello, this is Digvijay. Sorry for the delay. Am I audible?
Yes, sir, you're audible, sir. This is Navin from NPTL.
Yeah, there was an issue with my Zoom actually, so I got a little delayed. Sorry. Yeah.
Yes, sir. We can start
Yes.
the session.
Sure. I'm here. I do I have to write something? No, right?
No, sir, nothing.
Okay. I'm on my phone because laptop was giving an issue. It's okay, I guess, right?
Yes, sir, it's okay, sir.
Okay.
So, any TS joined here?
Yeah, I have a question already. Can I answer that or? Uh,
Yes, sir. You can answer that, and I'll paste that Google form questions here, sir.
sure.
The
So
chat
there is
box.
a question from Bhuvnesh who says, what is the difference between space charge and depletion and metallurgical junction? Are they same or different? So actually, I'll tell you, space charge region is the same as depletion region because it means that your region is devoid of any mobile carrier. That's called depletion region, and that's also called a space charge region. Okay, but space charge you can also use for insulator or like non-insulator dielectric, for instance. Okay, if you have a dielectric material, you can call it as a space charge region. You don't use the word depletion there all the time, but it's the same thing in a way. Depletion you use mostly when you have a semiconductor which is kind of doped and you are applying a bias or applying a field or something to deplete it of carriers. Essentially, it's the same as space charge, but the usage of the word might be slightly different. Metallurgical junction is a different thing. It need not be depleted. Metallurgical junction is a junction which is physically formed by two different material, not material, two different layers. It could be same silicon, but maybe p-type and n-type. Maybe p silicon with p gallium arsenide. Maybe a metal with n-type gallium nitride. Any physical interface between two material of different doping or different type, that's metallurgical junction. Okay, so I think I have answered your question, Bhuvnesh. So Venkateshwara Rao Busani has asked, can I get internship offer at IISc if I get 90% in NPTEL exam? There is a policy of NPTEL that if you do well in the NPTEL exam, you get an internship. You can get an internship with the faculty who gives this. So theoretically you can, but practically it is difficult because I'm on a sabbatical leave this year. So I'm not taking any intern this year. So I cannot have an intern this year, but you can approach other faculty members. Okay. Uh, there's a question from Logesh. I'm interested to learn new subject, but I find less confident after learning the subject. Why am I facing such an issue? And based on your experience, can you tell your way of learning new subject for getting expertise and confident with what I try to learn? Okay, this question is not pertaining to this course, but I'll still try to answer that. If you want to get confident after learning something, no, you need to learn it for a really long time. So typically, you have to spend 10,000 hours doing something to become an expert at doing something, whether it is learning to play basketball or swimming or semiconductor device or data mining or anything. You have to spend 10,000 hours to become an expert on that. Okay, if not 10,000, at least a few thousand hours to become comfortable. So if you're learning a new thing, for instance, maybe you're learning about, I don't know, biology, maybe DNA, or maybe you're learning about artificial intelligence or something, you have to spend a lot of time reading, going through online resources, books, talking to experts, taking courses, etc., for a reasonably amount of time, 6 months to a year, very focused. Then you can be confident of learning that. If you just read one book and give up, that will not help. Okay. Second question is from Logesh again. What are the opportunities in semiconductor industry? What are its prerequisites and roadmaps? This question is also not exactly for this course, but I'll try to answer. Semiconductor industry in India, I'll talk. It has been seeing a lot of investment from the government. A lot of fabs are going to come up, packaging facilities, CMOS fabs, compound semiconductor fabs, etc., etc. So I think the future looks very bright. There's going to be a lot of opportunities that are coming up, and these opportunities could be very diverse. We need people from mechanical engineering, chemical, computer science, electronics, electrical, metallurgical sciences. We need people from all background at all level. We need diploma holders, we need undergrads, we need postgrads, we need PhDs, we need everyone equally. They're very important. So there are all these different jobs with maintaining the clean room, with running the clean room tools, with characterization, with packaging, with dicing, with simulation, with design, with fabrication. There's enormous and infinite number of opportunities that are coming up. So it's good, I think. Prerequisites, it depends on what kind. For instance, you want to be a clean room tool operator, maybe an undergrad degree with some diploma and some background is okay. Maybe you want to be a chip designer, then you need to do some MTech in VLSI or something, maybe undergrad. So it depends on the particular thing. What are the standard simulation tools to learn to advance our career in semiconductor industry? There are so many different facets or aspects of semiconductor industry. It's not one simulation tool or one area. For instance, for device simulation, you can do Silvaco or Centaurus. For chip design, you can do Cadence or PSpice. For RF system design, you can do maybe ADS. For electromagnetic simulation, you can do HFSS. Cadence is there. Of course, layout design. There are too many simulation tools because there are too many different areas. You want to do packaging, you want to do thermal simulation, that's a different simulation. You want to do VLSI, that's a different simulation. You want to do you want to simulate the material process, that's a different simulation. So there are different tools. Okay, what are the web resources that you recommend to learn the researches about upcoming electronic devices and other electrical stuff? It's too diverse. I will not be able to say about everything because see, semiconductor technology has different angles. The biggest is the processing and the logic memory. So for memory devices, there's one set. There's logic and low power, processing. That's one another thing. There is power systems now coming up. Everything, electric vehicles, everything is again semiconductor. There is radio frequency. There is optoelectronic LEDs. There is organic LEDs. There is displays. There are just too many different areas of semiconductor itself. So it's not one source. For each of them, there will be like 100. Just pick up one, say chip design or maybe LED. There'll be like 100 different web sources. It's impossible for me to recommend. You have to just keep looking up and that level. Some of these resources could be for layman, someone just wants to just generally get a feel for what the field is. Some websites could be for really experts. You want to really understand the details. Then you have to read books. You have to take online courses. You have to go to classes. You have to talk to people. You have to go learn hands-on on the ground, things like that. Okay. Kavin Kartik is asking, what is the question pattern for the final exam? It's MCQ, multiple choice question. Do all the questions asked in the exam based on assignment? Partly, it will be based on the content that has been covered. That's it. It's multiple choice. Will you select the toppers for internship? I don't offer internship actually. I told it already. So I don't select internship. I'm on a sabbatical leave actually from ISC. This year, so I'm not offering any internship for any Intel. Okay, how can I study for GATE exam from first year of college? I don't know because I did not appear for GATE myself, and I don't teach for GATE, and I also don't set the question paper. I don't evaluate, so I have no idea. But I can tell you that if your concepts are good, then you will do it. You also need to increase your speed while solving questions, but I think looking at previous year's question paper and trying to build the concepts really strong, that will help you. But clearing GATE should not be the objective in life because I feel many people who do not have concepts, they also clear GATE with good ranks because of the coaching and other things. But then once they join PhD or something, then they really, really struggle because they don't have the good concepts. It also has happened. So I would say build the concepts and love the subject, then you will be good. Okay. So I'm waiting for more questions. Okay. If there's any repeat question, you can ask. I'm here. Okay.
Hello.
Yeah. I cannot.
Yeah, I have a doubt which book I should refer for this course. Am I audible now?
You are audible, but your voice is kind of breaking down.
One second, I'm in class.
Hello?
One second, sir. Hello, am I audible now, sir?
Yes.
Yeah, so I want to know which book I should refer for this course.
You want to know what? I'm so sorry. It's just breaking out. Book. Are you asking about the book?
For numericals and stuff. Yes, sir. The book we should refer for this course.
Okay, there is not one book. There are many books. There is this book by Umesh Mishra and Jaspreet Singh called, I think, I forgot the title of the name, but you can just look for Semiconductor Device Book. by Umesh Mishra and Jasprit Singh. I have referred to that book a lot. It has very, very interesting numericals, maybe unsolved. Most of them are unsolved, but it's good. You should read that book. There is also other book like MS Tyagi. There is a book called.
Yes, Mishra.
Sorry.
Could you repeat the first?
Can you please? Can you please? I cannot hear you. Whoever you are, can you please type your question so that I can read the question? Which book should we refer? So, Umesh Mishra and Jasprit Singh. MS Tyagi. So I have written down 3 books. I forgot the name of the books, but you just type in Google the name of the author that I have mentioned plus semiconductor book. That's it. Okay. So actually, there are many, many very good books. These are 3 books that I mentioned: Umesh Mishra and Jasprit Singh, and one book is by MS Tyagi. One is by SMZ, and these 3 are really good books. There are other good books also, but I think these 3 are good enough for now. Okay. Currently, I'm referring. So, Kasap, is it a good book? I don't know a book called Kasap. I have never heard such a book. Okay. You have to read good books. So, the 3 books I mentioned are really good. You can go through them. Okay. Okay. I'm here. Okay. If you have more questions. Okay. I am a computer science student and I really love the more hardware side of things. I'm doing this course. I can understand most of it qualitatively and most of the formula and how they come out, but the sheer number of formula is daunting. Remembering the formula is going to be important for the exam. But outside of that, how beneficial is it to have this formula at my fingertips? I don't know if my exam is open book or not, but I usually keep exams open book. Uh, because I believe that memorizing formula is useless in today's world, where all the information is there in Google, literally one click away. I think any course or any exam that asks people to memorize equation or formula is a useless course or exam. Okay, I think like that. So I don't know if this course still has a closed book exam, but I generally advocate open book, open internet, open chat GPT, whatever you want, because in reality, when you actually solve problems, you have all the resources to yourself. It's not like someone will give you a project in the real industry or in real academy or something. Try to solve this problem of energy or some water crisis problem, but you don't use Google. Nobody will say you like that. You have all the equation, you have all the information, all Google to yourself. Idea is to come up with innovative solution, insight, intuition that will help solve the problems or come up with new ideas. Okay. So I don't think it's useful to memorize any equation in reality. You don't need to. Okay. I don't remember the equations myself. If I teach them all the time, then I naturally tend to remember, but I don't remember them. Okay. So I don't care, and you shouldn't care either. But if you know the equation, what the benefit it gives you is that, well, not the equation, but the relation between two physical quantity. How, for instance, how depletion changes with doping. Okay. That kind of relation is good to remember. It will help you design new device. Suppose I want to come up with a new transistor. I want to come up with a new LED design. If I know how doping and field changes, then I can come up with a better design. So I don't need to remember the equation, but I need to know the relation between different physical quantity. Am I getting you? Just give me a second. Okay, I'm getting an urgent call from my home. So just give me a second. Okay, I'll be back in just 1 minute. हाँ फोन করেছিলি हाँ ক কার্তিক ক বলু কাৰ্তিক শুনিছ নাই তই हाँ ক বলু ক বলু Hello. Okay. So there is a question on early effect. During reverse bias, the base width reduces and collector width increases. Is the reason base doping is no? Actually, not like that. If the base doping is lighter than collector, see the depletion will extend predominantly to the layer where the doping is lighter. If the base doping is lighter than the collector, then in a reverse bias, the depletion will extend more towards the base. As a result, early effect will become strong. If your base doping is higher than the collector doping, then your early effect will not take place as much because your depletion will not extend to the base so much. This is the reason why the collector is doped lighter than the base. It's called subcollector, so that the depletion is going towards the collector only, not towards the base. And below the subcollector, you have highly doped collector for the good contact. Okay, I hope I could clear that. In BJT delay, how base charge has take place and how charge can create delay in base in BJT? Okay, good question. So Gandhi is asking, Jeet Gandhi. So in BJT, there's a delay called a base delay. Okay, so there are two components to it actually. The primary component is that you're injecting minority from the emitter side to the base, and those reach the collector and give you the primary current. You know that, right? So when these minority carriers are injected towards the base, the minority storage, charge storage in the base, they take some time to charge and discharge, or you can say they take some time to flush out. In a PN junction, you're injecting before biasing the base emitter, so you're injecting the charge, minority charge to base. So how much time you're taking to flush the charge out? That's your BJT, base delay. And effectively what it means is that the total charge that is stored in the base, minority charge, divided by the current that is clearing the charge, that is your base delay. So the base charge, minority charge, divided by the collector current, that is your base delay. Okay, that's your predominant base delay. The second aspect is the electrons physically travel across the base, no? So that also creates a slight delay. So that is given by the width of the base, the actual base, not the neutral base, okay, divided by the velocity of the carrier, the saturation velocity of the carrier. That also gives you a delay. So these are the components that give you the base delay. Okay, I hope that would clear your question. Okay, I'm waiting. Okay. Okay, I'm here if there's any more question. Oh, there's one more question. Sorry. Chandranu Dhaval has asked this question. Why are the dopants usually differing in plus minus one electron from the element being doped? Why are elements with higher differences not usually used? I mean, you want either to give one electron or take one electron. If you take higher elements, no, it is not easy to take away two electrons. It's not that easy. And this thing actually, although it used the simple hydrogenic model, key, it has given an electron, it has taken an electron, it's not that simple. This actually dopant introduces some ionization energy levels. Okay, so if you use higher elements in the periodic table, it's not like each will give you two electrons. It's not that like that, because the amount of energy needed to break away two electron or take two electron will be enormously large, and the ionization energy may not correspond to a favorable position in the band gap. You might spend more energy. That's not energetically favorable. Okay, so it's not like if you use a higher element in the periodic table, you will get more electrons. Okay, that simple model doesn't hold true actually. It has to have a particular ionization energy. So that being said, people do use in compound semiconductors specifically, say gallium nitride, you can use carbon as a dopant. Carbon has a 4, as a group 4 element, and carbon as a dopant is not to dope it n-type or p-type, but carbon is used as a compensating element. What it means is that carbon will take away the electron. It will eat away the electron. It will compensate the electron. Why is that? That will help you make it insulating. Otherwise, gallium nitride has a lot of background n-type that makes it leaky. So you add carbon as a dopant. It's an acceptor like dopant. So higher order elements are used specifically in compound semiconductor, but again, it's not that simple as we. Okay. So I'm here. Sorry.
Arun.
Yeah, I'm in actually a live call.
Okay.
But you can tell me, is there a question?
No, sir. I actually wanted to speak your plan and I mailed you last week.
Did you need some files?
Yeah.
Oh, I didn't bring the hard drive. I'll bring it afternoon. Are you free today? No.
2 to 5 I have that.
Just send me a reminder in the morning of the day, like 8 or 9 o'clock. So when I come from home, I'll bring the hard drive.
No, just tell me which time you will be here.
No, if I don't have the drive, then there's no point. No.
Yeah.
So just remind me so that I'll bring the drive here so that it is here.
This time? Tomorrow?
Yeah. Sounds good. This time tomorrow.
Yeah, nice.
Around 12. Okay. Yeah. Okay. In equilibrium, you have taught about the slope in conduction and valence band. So I want to understand what happens if Fermi level has slope. That condition is not in equilibrium? Yes. So if the Fermi level has a slope, it means it is not in equilibrium. If the Fermi level has a slope, it means there is current that is flowing. Okay. At equilibrium, when current is not flowing, the Fermi level has to be straight, no slope. Okay. Yeah. I'll come. Does this mean that in forward or reverse bias, the EF has a slope? Well, the slope in the Fermi level will be there, but it is very, very negligible. Okay, because it depends on the quasi Fermi level and the change in carrier concentration. We assume that outside the depletion region in a PN junction, outside the depletion region, the neutral region, the so-called neutral region, the charge is varying very slowly. That's the assumption we make, which is why the Fermi level slope is also very, very slowly changing, which is almost like no change. But there is a change, but it's a very small change because the assumption is that the charge is not changing as much. If you have very high injection, very high current, then yes, it will change even more strongly. In the depletion region, the Fermi level will change. We call it a quasi-Fermi level. So the whole Fermi level and the electron Fermi level will be split. That splitting is equal to the applied voltage. Instead of a slope, you have a split in the Fermi level, which also bends, by the way. That gives you an indication that there is a charge flowing in the depletion. Outside the depletion, we assume neutral. So the Fermi level changes very, very slowly, almost like not changing. But in reality, whenever there's a current, there's a change in Fermi level. Okay. This means applying biasing will create slope in Fermi level. Yes. If you apply bias, Fermi level changes. That is the reason why in forward bias or reverse bias, the PN junction, your Fermi levels will split and will make a quasi Fermi level hole, quasi Fermi level electron, and they are different. Away from the junction, the Fermi level appears to be straight because the charge is changing very slowly. The moment you go to very high charge injection, very high current, then your Fermi level changing slope will become more pronounced. Okay. In PN junction under equilibrium, carriers are moving due to difference in concentration. So diffusion current exists, but how drift current happens is net current is zero. In PN junction under equilibrium, the drift and diffusion current are exactly equal and opposite, and they balance each other, and that's why there is no current. Assuming there is no light shining, no magnetic field. Okay, no light shining, no magnetic field, nothing. What happens is that the carriers try to move from P to N, N to P, because that's the diffusion tendency, but the drift will be opposite because the field is there. No, the field is such that it will try to oppose the holes towards the P side and electrons towards the N side. So it will prevent them from coming. The field will prevent. What is the difference between a normal PN diode and a Zener diode? And what does Zener breakdown mean? Zener breakdown means, or Zener diode means, you have a very highly doped P type, you have a very highly doped N type. So the depletion is very narrow. What it means is that they will easily tunnel and create a very high leakage, and the device breaks down. So Zener breakdowns means there is a very high tunneling current that happens because of the high doping that you're using. It breaks down at very few volt, like maybe 4, 5, 6 volt, it breaks down. And Zener diode is that diode that utilizes this principle. So Zener diode is only for limiting the breakdown. You know, like if you want that it should not go above a certain voltage, like 4, 5 volt or something, you put a Zener diode. Like that's the voltage it can drop. Below above that it will leak. So that's the Zener diode. Okay. Sir, please suggest NPTEL course next to this course. I don't know. There are other faculty members from IISc or maybe IITs who offer very good semiconductor device courses. You can take them. I don't know exactly. I have offered another course this sem. It's ongoing. It's a bit advanced course. It's called Basics of Semiconductor Microwave Devices. In that, I talk about a little bit more advanced semiconductor devices which are used for RF or microwave electronics. I don't discuss about circuit or microwave engineering. I talk about devices, but little bit more advanced, which are used for RF. Okay, so you can take a look at that course. Sir, I'm not getting how field exists in equilibrium. Field can exist in equilibrium. Internal field. You're not applying any external field. You're not applying any external voltage, but internally the field can be there. See, for a field, there has to be some charge. If there is some charge, there will be a field. Why? Poisson's equation. Poisson's law tells you that the moment you have some charge, you will always get some field. So you are going to get some field whenever there is a charge there. Okay, that may not give you current because the opposing fields might, or opposing diffusion current might make it zero. But the moment there is a charge, there is field. Now in the neutral P region or neutral N region, there is no field. Why? Because the total number of mobile charges there is balanced by the total number of ionized impurity. That's why the charge is zero. Only in depletion there is a total charge, and that's why there is a field. Okay. If the holes say as the absence of electrons, how does EK diagram, mobility and other stuff have derived of absence of electron, and how does absence of electron creates higher effective mass than electron? It's a good question from Jeet Gandhi. Actually, the fact that holes are absence of electron is a very simplistic picture we build to explain holes and positive charge, but it is not that simple. It is a very, very complicated quantum mechanical concept. It's the many-body manifestation of the absence of electron. When electrons are absent, the interaction of the many-body things there, it gives rise to these holes. They are quasi-particle. They are not exactly absence of electron. Yeah, they are absent of electron, but it's much more to that, more than that. Okay, it has got to do with the bands of the crystal, the quantum mechanics of the same. So that gives rise to the mass. You can imagine the absence of electron moving. It's like electrons are moving in the opposite direction. So overall, you can think the mass is higher. So the EK diagram, everything is derived based on this quantum mechanics. It's, as I told you, it's a representation of the absence of mass, simplistically put, but actually it's much more complicated than that. Okay, and it was not very well understood until maybe 50, 60 years back. It's very complicated in a way to understand holes. Okay, because for instance, all metals have electrons. So when you do a Hall effect measurement, you should only get N-type carriers in metal, but certain metals give you P-type carrier. How can electrons give you P-type in metal? in Hall measurement. It was not explained successfully until quantum mechanics, maybe 60 years back. So it has got more to do with that. Okay, it's not very simple. Can we expect any course on modern devices like HAMT and CFET in NPTEL platform? I am not going to offer any course on PFET or negative capacitance FET because I'm not an expert on that and I don't work in those areas. I don't have much idea. So you can see if there are courses that other faculty or professors are offering on negative capacitor FET or tunnel FET, maybe from some IITs, maybe from ISC. You can check. I'm not going to offer, but maybe some other professors might offer. I do have a course running this semester called Basics of Semiconductor Microwave Devices, which is an advanced semiconductor device course specifically for devices that are used in RF or microwave electronics. In that course, I am teaching about HAMT in great details. Okay, so you can take a look at that course, Basics of Semiconductor Microwave Devices. In that, I cover HAMT. Okay, hope that answers your question. What is the best to prepare the examination for this course? You just understand the concept, that's all, nothing more. If you know the concepts, you will do good. No questions asked. Okay. Okay. We still have some time. If any of you have any questions, I can still try to answer. What happens when you dope silicon with +2 or +2 ions? I think it will not accept. Say, as I told you, it depends on the ionization energy, the donor or the acceptor ionization energy that is introduced by the element in silicon. You cannot randomly add a +2 element there and you cannot expect that it will give 2 electrons or take away 2 electrons. It depends on the ionization energy. Okay. So I cannot tell you exactly what ionization energy it will have. Maybe you are adding gadolinium, maybe you're adding niobium or something to silicon. What it does to the ionization energy, you cannot predict like that. You have to do simulation. I mean, these are called density functional theory ab initio. In that, you have to find out theoretically what is the donor ionization energy when you add some element, in silicon, for instance, maybe gadolinium or something. Okay, so it's not always. It is very unlikely that it will donate or accept 2 electrons because it depends on the ionization energy. Okay. Hmm. Maybe I'll wait for 5 more minutes and then we'll wind up. Okay, a few minutes, maybe 2-3 minutes more. When we say a current is flowing, which we say with respect to electron flow in the valence band and electron flow in the conduction band combined. Well, in semiconductor, current can be either due to electrons or holes. So current due to electron is because of electrons flowing in the conduction band, not in valence band. And current due to hole is because of holes flowing in the valence band. Okay, that's how it is defined in semiconductor. Okay. BV Rao, sir, please suggest NPTEL course to continue after completion of. I already told this. I actually not offering any conventional semiconductor course. Other faculty members from IIT or ISC may be offering. So you should please check that. However, I am offering another course this semester, which is running in parallel now. It will run for next few years also, hopefully. It is called Basics of Semiconductor Microwave Devices. This course is not about circuits or systems or microwave engineering. This course is about semiconductor devices of advanced semiconductor devices, which are specifically used in radio frequency or microwave electronics, like high electron mobility transistor, HEMT, gun diode, impact diode, HBT, okay, LDMOS, silicon, some of the CMOS, RF CMOS, etc. I'm offering that. Okay, you can take a look at the course. Okay. 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 In a semiconductor device, when electrons move from valence band to conduction band, electrons in valence band also have space and tendency to move in valence band due to space available. Precisely, you're right. That is called hole. Whenever there is space available in valence band, whenever there is a vacancy, we call it hole. And electrons traveling, we don't call electrons traveling, we call holes traveling. It's like an air bubble, coming out from air water, inside the water. So holes will move in the opposite direction to the movement of electrons. So any vacancy that is there, now we call it holes, and the holes will move. Okay. Sounds good. Can we call this current in valence band? Yes. This is precisely called hole current. We call it the hole current. Okay. Okay, if there's no more question, I think we can close this. Okay, so if some of you had any questions you're not able to ask or you don't feel good to ask, you can always email me, digbijay@isc.ac.in. It's in there. I always try to reply answers to email. If I miss the email and I do not reply, wait for 48 hours and again send an email. Okay, I'll try to reply. Okay. So, Mr. Naveen, I think we can close the session. Okay.
Yes, sir.
Okay. So, is there anything else? I can just wrap it up now. Okay.
Yes, sir.
Okay.
Any
Thank
future
you.
question that we can that will come in Google forum? We
Sure.
can
Sure.
in the
Thank you.
forum.